Hi, friends. Let's talk about some interactions between objects that, in which, I should say, motion is not limited to one dimension. Here we're letting objects move in a plane, a two-dimensional plane. All right, and we'll go through two ways of looking at interactions. Um, One I sort of refer to as the vector requirement, and the second I refer to as the component solution. All right, so one way is, really talks about what must be true just from a pure standpoint of physics, and the other way is sort of about here's how you're going to solve. All right, so when we look at these two objects, and these we're saying are going to hit and stick, okay? Um, it's called a perfectly inelastic collision. So object one, object two, incident upon each other with um, what I'll call P1 initial and P2 initial. These vectors represent the object's momenta. And these two things hit and stick together. So what we can do is talk about what happens, what must be true after the interaction. And as some of you know, this is my before and after delineation, this dotted line here. So afterwards, what must be true about this system? Well, what must be true, the vector requirement is that when objects interact, because they apply the same forces to each other for equal amounts of time, that equal and opposite forces, I should say, that means they each experience equal and opposite impulse or equal and opposite change in momentum, which means the system's net change in momentum is zero, which means that the system maintains a constant amount of momentum. There's a same amount of momentum initially and finally. And remember, momentum is a vector. The direction that momentum vectors point is of a lot of importance. All right, so what happens is, well, look, this, come here, won't you? Can't you? Here you go. This vector here is number one's initial momentum. Bring that over here. This vector here is number two's initial momentum. And so this, notice I'm adding these tip to tail. That's a vector addition. And this vector is the net initial momentum. Right? Well, what must be true? It must be true that that momentum and the final momentum are the same thing. All right, and so what we've actually found is that this clone is the same is really, I'll just change this right to final. Because if that was what the momentum was in the beginning, then that's what the momentum has to be in the end. Kind of end of story. All right, so when we talk about momentum vectors, we can add them tip to tail just like we add any other kind of vectors, right? And then we apply our conservation statement that says what you have in the beginning, what you have in the end have to be the same thing. This is actually an easy vector addition. This is a right triangle, so we could say something like, our net initial momentum would be the Pythagoreization of those two initial momentum vectors. Well, and therefore that's actually the final momentum also. All right, and we could express this angle, of course, as something like probably the inverse tangent of one initial. Yeah, look familiar? All right, it's pretty common also, especially in this hit and stick sort of case, right? If this is the final momentum, we could also express this, right, that the final momentum is the two objects. And I'll go back to vector. Important to notice that the velocity of a system or object is in the same direction as its momentum. So we could use, very typically a question might ask, what's the system's final velocity? You just take the system's final momentum, in this case, divide by the sum of the masses because they're stuck together moving at a common final velocity. Okay? Now, this is sort of a special case where we get this nice right angle thing. So it might really not be the most appropriate to apply what I call the component solution here. But the component solution means that when we say, very generally that momentum has to be conserved, what we really mean is, if we look at it from a component standpoint, that momentum has to be conserved in each of two, in our case, perpendicular directions. Why two? Because we're saying we are limiting still these interactions to two dimensions, P final Y. Okay? And so, again, like I said, since this is a pretty standard or pretty simple case where these two initial momentum vectors happen to be at right angles, this might not, this might be a little bit of overkill for this sort of case. But what you can do is say, well, again, if this is P1 initial, and this is P2 initial, well, when we do a conservation of momentum in the x direction, it looks like it's only P1 initial. Well, that's the net final x momentum. All right, when we look at y direction, you might really say, like, I don't know, negative P2 initial, because, maybe we're going to use our standard sort of positive Cartesian coordinate convention, right, equals the net final y momentum. So what we can do is construct our final momentum vector by knowing what its components are. Well, its x component is the same as P1 initial. Its y component is the same as P2 initial, and therefore here's the net final momentum. Well, notice that's the same exact thing we did here. We just added the two vectors, right? Here's P1 initial, here's P2 initial. All we do here is sort of say that this is, well, we're constructing the components of the final momentum. All right? You get the same answer, of course. That might make a little more sense when we look at a problem like this, where, the vector requirement still holds, in that if this is P1 initial, and this is P2 initial, right? Here's object 1's initial momentum. Here's object 2's initial momentum. Here's the vector addition of those two, the tip-to-tail addition of those two vectors. Well, here is the net initial momentum. Well, the vector requirement, again, is that the net initial momentum vector and the net final momentum vector have to be the same thing. So that says that when we find this, what we've actually found is this. All right? And like we said a minute ago, pretty typical to say, well, notice what I'm going to say is, well, this is actually the final. And I'm going to drop the net because we're saying these two things hit and stick, so we might as well just talk about the system's combined final momentum. Fair enough? Now, in this case, because these two vectors, the two initial momentum vectors, aren't at a right angle, you can't just use a geometric trick like Pythagorean theorem. But what you can do is solve this with what I call a component solution. Now, when you do that, right, we say, well, we start here, and then we say in each of two perpendicular directions. So initial x, final x. And we say initial y, final y. And then what you really might do is we say here's one initial. Now what we do is we say this has an x component that looks like that. P1 initial x. P2 has a little tiny like that P2 initial X. And here's P1 initial Y. Whoops, P2 initial Y. Notice we're being careful about drawing our components in the right directions. And then maybe we call this like theta 1, and we call that theta 2. And now what we say is, okay, let's see, all the initial X momentums. Well, that is P1 initial X for me minus P2 initial X. Notice that we're using this standard convention where right positive, left negative, up positive, down negative. All right, so we would find the magnitudes of each of these two components and then subtract because they're in opposite directions. All right, and that's going to give me the net final X component. So we're constructing the components of the final momentum. All right, and you know, this really looks something like, well, here's P1 initial X, and I'm actually adding, yes, P2 initial X. So the final X momentum is that long. So in the end, this system has a horizontal component of momentum that looks like that. And we could actually find this, you know, what we really do here is probably something like, well, not probably, but we would say, let's see, P1 initial X, that's M1 V1X. This is M2 V2X initial. And I would say something like M1 V1 initial cos theta 1. M2 V2 initial cos theta 2. Net, or just, you know, drop the net, that's okay. Same thing. Yeah? And then we do something very similar with the Y component stuff. I would say there's a P1 initial Y pointing up, a P2 initial Y pointing down, so I call it negative, is net final Y momentum. I'll skip this intermediate step, but I would write this as M1 V1 initial sine theta 1, M2 V2 initial sine theta is the net final Y momentum. Right? And quite literally what we're doing is saying here's P1Y, here's tip to tail P2Y. That might be a little too long, right? A little bit. Whoops. Come on, I want to shrink, and I can't do it. I'm picky. I can't leave well enough alone. P2, sure, maybe that long. Is that better? Yep, great. So add those tip to tail, and what we get is a final, that's ugly, a final vertical component of, so there's the net initial Y. That means it's equivalent to the net final Y. We add those two components up, right? This is the net, well, initial and final. It's the net X momentum. They're the same. Here's the net Y momentum. So that means that it's actually before and after. That's the net momentum. You want to call it before or after? I don't know. It's the same thing. I'll call it final since we are looking after the collision, but it's the same as the initial. All right. And what I want you to notice is that if we take this vector and we look at, yeah, this vector, which came from just literally adding up the two vectors, tip to tail. I mean, this is more of a what people maybe call an analytical method, where you have to jump through a bunch of algebraic and trigonometric hoops to get there. But that's how you will solve a problem. Unless you want to get out your ruler and protractor and draw things to scale, people don't do that. People do it, but You're not going to do it in an examination sort of environment. And the one thing that we haven't said so far or yet is that once you have each of these components of the final momentum, well, what you then do is say the actual total final momentum is the net x plus the net y, right? We build a nice right triangle out of these two components, and then we use Pythagorean theorem. And you want this angle theta here, theta final? Well, we'd say theta is the inverse tangent of the net y over the net x. Why am I dropping initial and final now? Well, because the straight physics part of it says that it doesn't matter if you're talking about initial and final, the net is the same, the total is the same all the time. Okay, so when you're posed with, a quote complicated problem, this is probably the approach you're going to take. Again, if you're not using a ruler and protractor, and you're not. Let's be honest. Okay. Gets a little, maybe more complicated here. Maybe not. I don't know. The vector requirement says that the initial momentums added up give you, a little too big, give you some net initial momentum. Right? Pretty good, right? Yeah, that's fine. So here's the net initial momentum. Well, guess what that is? It's the same thing. The vector requirement is that the net initial momentum and the net final momentum are the same thing. So this is actually the net final momentum. And what that says is if now this is a different case. These are hitting and bouncing off of each other. So we got two separate momentum vectors before the interaction, two separate momentum vectors after the interaction, right? I've detailed one of them for you. Here's one of the vectors after. So what we're saying is that this vector plus number 2's final momentum vector has to give you this sum. So apparently, if we were to add this vector with this vector, right, we're adding P1 final plus P2 final. Excuse me. Notice that the net is the resultant of those two vectors. So apparently, well, this is a pretty darn good representation of what number 2 does after the interaction, if the system has to maintain a constant momentum. All right, so that's just sort of analyzing these as vectors. How do you do this with the component solution? Well, it gets a little bit loud in terms of the number of steps and stuff that you have to go through. What I'll do is say, the first thing we're going to do perhaps is say that the initial x momentum and the final x momentum are the same thing. What I'm skipping is saying momentum's conserved, and that means momentum's conserved in both of two perpendicular directions. So, well, the nice thing here, let's see, P2 initial. I'm going to look at everything in terms of components. That's a little big. That's a little better, fine. This is P1 final Y. This is P1 final X. All right, and then maybe here's like a theta 1 final. Well, the net initial momentum in the X direction is actually just P1 initial. So that equals all of the momentum vectors in the X direction at the end. All right, and that means that it's P1 final X and P2 final X. right? You'll notice in the beginning we have this much. Come here, would you? This much, yeah, this much x direction momentum. In the end, in the end, in the end, we have one object has this much. So the other object must have this much in the x direction. That's what this expression says, right? So I'm sort of mixing a graphical and an analytical method here, which you really wouldn't do if you're just solving a problem, but it's worth illustrating. All right, so what we're saying here is we can construct the final momentum's component by saying, well, this would be P1 initial minus P1 final cos theta 1 final, perhaps P2 final x, right? Or this is like fine, you know. And for P you do MV, right? This is final x, right? So like, you know, if this is 10 and this is 4, then this is 6, duh, right? And in the y direction, well, we do the same thing. We'd say something like net initial y net initial y is net final y. And then we'd say, well, it looks like that's negative P2 initial is negative P1 final y. Yep, final y. Now I'm just going to leave it as plus P2 final y. And what that says is I can let, you know, since I just leave this as plus, I can just let the sign of my answer for P2 final y tell me if P2 final y points up or down, right? Or P2 final y is negative P2 initial plus P1 final, well, how about this? Sine theta 1 final. Sure, final. All right, and I think I kind of arbitrarily chose this not really great because, well, okay, I mean, it looks like P1 final y is a little bigger than P2 final y. So that means there was this amount of vertical momentum in the beginning. Now there's, well, one of them has that much more in the end. So it means that P, yeah, that guy's got to have that much momentum upward at the end. All right, in order for our final y components to add up to our initial y component. So here's the, let's see, this is P2 final x. This is P2 final y. Here is our P2 final. And again, if we want to actually calculate how big P2 final is, the nice thing is we've constructed the components of our final momentum vector. We can use Pythagorean theorem to find the whole darn thing. We can find that angle using some trigonometry, the inverse tangent. All right, but just so we're sure, right, here's the, well, there's a lot grouped up there, but this vector, we're saying, is the final momentum of object 2. Well, let's look at when we just went through this, you know, just the vector addition, yeah, we said it's that vector. Let me copy that. And then let's go over here and let me paste that. Compare. Oh, yeah, look, they're the same darn vector. Boom! Okay, so while this way is nice, you know, just as a way of looking at things and doing perhaps a quick sketch of what might happen, this is the way that you solve problems, right? You conserve momentum in each of 2 perpendicular directions. Okay? All right, folks. See you soon.